In this video, we're going to discuss even and odd functions. So we'll start with even functions. So if we say a function is even, what that means is that if you input two x values that are opposites, you get the same y value for the output. And so that's what we're showing here with two different types of notation. You can look at it as if the point x comma y is on the graph, then the point negative x comma y is also on the graph. So opposite x values, but the same y value. We can also describe this with function notation. So here, remember f of something is a y value. So what we're saying is we've got a y value on the left side, we've got a y value on the right side. Those y values are equal. So we're saying that's the same y value, just like we showed here. And if you look at the inputs, so what's inside the parentheses, one says negative x and one says x. So that's showing the same thing that we showed in the first line. Opposite x value gives you equal function values or y values. And what happens is you can see, so we've got an even function here to use as an example. If you look at the table, you can kind of see this playing out, right? So if I use an x value of -1 versus +1, I'm getting the same y value. Both of those have a y value of -3. -2 and +2 have the same y value of 0, and that happens for every x value. We are only showing obviously some of the points in the table here, but because it's an even function, this would be true for any x value. If you plug in an x value and then you plug in its opposite, you're going to get the same y value for both. And what happens when we graph this is we start to see some symmetry. So I'm going to just plot a few of these points here. So we've got 0, 0, we've got -1, -3, and then 1, -3. And then we'll go ahead and plot -2, 0, and +2, 0. Now there are points that I didn't show in the table, so you could plug in an x value of 1/2. And if you plugged in -1/2, you'd get the same y value that you got for +1/2. So what we're going to see then is this symmetry. So if we draw in the right side of the graph, it's just going to keep increasing to the right there. What we're going to see is the left half is symmetrical to the right half about the y-axis. So we've got our vertical y-axis here. You can think of it as if you took your paper and you folded this in half on the y-axis, the left side and the right side are going to match up exactly. My drawing's not the best there, but you get the idea. So if we're curious, if we're looking at a function and we're saying, okay, is this an even function? One way to tell is by looking at that symmetry. If you see that symmetry, you fold it in half on the y-axis, the two halves would match up. That's a good clue that it's an even function. We can also show algebraically that a function is even by using the function notation that we discussed earlier. So showing if I substitute in the opposite x value, I get the same y value. Now we can't just show that for one x value or even for a few x values. That doesn't really prove anything. But if we use this function notation, we can show that it would happen for any x value. So for example, we've got a function here, f of x equals x squared minus 5. So what we're going to show is if I substitute in the opposite x value, do I get the same y value? In other words, does f of -x equal f of x? So everywhere that we see an x, we're going to replace it with -x. And then we're going to see what happens. So since we're substituting in something negative and there's already an exponent there, we're going to need parentheses around that. And then what we need to do is we need to think about what happens when we square a number. And you can use an example if you want. So if I plug in 3 for x, right, 3 squared is 9. If I plug in -3 for x, I'm going to square it, which means I'm going to multiply it by itself, right? So negative times a negative is going to give us a positive. So regardless of whether we're squaring a positive or a negative, we're going to get the same thing. So in other words, 3 squared is the same as -3 squared. 5 squared is the same as -5 squared. So since that's the same, we can just write it as x squared. We're going to get the same output. And so what we get when we substitute in -x is we get our same function back, right? X squared minus 5, that's the function we started with. That's f of x. And so what we just showed is that f of -x equals f of x, therefore the function is even. We've got another example here. We're going to show this function is even. So we're going to substitute in -x. Everywhere we see an x, there's only one place to do that here again. And then we just need to think about what happens when you take the absolute value of a number. So again, think of an example. If x is 4, right, the absolute value of 4 is 4. The absolute value of -4 is also 4. So regardless of whether you use a positive or a negative number, you're going to get a positive result. So the absolute value of x is the same as the absolute value of its opposite. And so because those are equal, now what we see is we just get our original function back again. So we showed that f of -x is the same as f of x, and therefore the function is even. All right, we're going to move on to talking about odd functions. So here's our definition for a function to be odd. And it looks similar because we're looking at what happens when you use the opposite x value. So with an even function, we saw that using opposite x values gave us the same y value. What we see here is if we use the opposite x value, we also get the opposite y value. And we can see that here in the table. So if x is -1, y is 3. And then if we use the opposite x value of +1, we get the opposite y value of -3. Looking at the points where y is 0 doesn't really help illustrate this because 0 doesn't have an opposite. 0 you could think of as its own opposite, so the property still holds. But if we look at a different point, like -3, -15, for example, if we use the opposite x value, +3, then we get the opposite y value. We get +15 instead of -15. And that happens for any x value that we choose, so it's an odd function. Looking at the function notation, the left side is the same as what we saw before. We're seeing what happens if I use the opposite x value. So if I'm using the opposite x value on the left that I am on the right, we've got -x on the left, +x on the right for our input. So it's showing I'm choosing inputs that are opposites. What happens? Well, the y value I got before is equal to the opposite of the new y value. That's where the negative's coming from there. Odd functions also have symmetry, though it's a different type of symmetry than what we saw for even functions. So if we plot a few points here, I'm going to plot 0, 0, -1, 3, 1, -3, -2, 0, and 2, 0. What happens is we do get symmetry, but it's not the same type of symmetry that we saw before. So here's what the graph looks like. We do see symmetry, but it's not the symmetry we saw before. If we fold our paper on the y-axis here, the two halves don't match up. But this graph has rotational symmetry. So if you could pick up just the sketch of the graph and rotate it 180 degrees around the origin. So this point at the origin stays put, but this part is going to rotate and this part is going to rotate. Basically, take your paper right now if you've drawn this and turn it upside down so that like the words on your paper are upside down. It's going to look exactly the same. That's what rotational symmetry is. You rotate it about the origin 180 degrees, it looks exactly the same. This point down here, 1, -3, is going to come up here and be at -1, +3. So we can see a function is odd by looking at its graph, looking for that rotational symmetry. We can also show algebraically that a function is odd, just like we showed algebraically that a function is even. And that process is going to look similar because we're still concerned with what happens when I use the opposite x value. So we're still going to be substituting in -x everywhere we see an x. But if it's odd, we're not going to get our original function back. We're going to get the opposite of our original function back. Basically, we're going to get -1 times our original function as a result. So let's do that here with this one. So we're going to substitute in -x. And just like when you substitute a number for x, you're substituting it everywhere you see an x. So there's two places we need to do that here. And then it's just a matter of cleaning this up a little bit like we did before. So if you cube a negative number, you're going to get a negative result. Like if x is 2, right? It doesn't matter if I cube -2 or if I cube 2 and then make it negative. Because -2 times -2 times -2 is going to result in -8. So if we're raising a negative number to an exponent, basically the parentheses don't matter. So that's the same as -x cubed. And then here we're adding a -x, which is the same as just subtracting x. Now what happens is we got basically our original function just with the signs all changed. And we can see that if we factor out a -1 from every term, we'll be left with x cubed plus x, which was our original function. So we ended up with a -1 times our original function f of x, which is exactly what's supposed to happen if the function is odd. We've got another example here. If we substitute a -x into this function, so everywhere we see an x, we're going to replace it with a -x. The cube root is going to be similar to the exponent of 3. It's not going to matter whether the negative is inside or outside. If you think about if x was 8, for example, cube root of -8 is -2, but if you write it instead like this, if x is 8, you've got cube root of 8, which is 2, and then we're going to make it negative. So either of these, if x is 8, either of these results in -2. So they're the same. So we're going to write it like that just to kind of help us out for what we're trying to do here. We've got negative times a negative here, which is a positive. And so once again, we ended up with almost our original function, but all the signs are different. The first term was positive, now it's negative. Second term was negative, now it's positive. If we factor out a -1 from every term, that's going to change the signs, and then we can see that we ended up with -1 times our original function, which means our original function is odd. So we spent a lot of time talking about what makes a function even or odd. The reason that's so interesting is because most functions are not even or odd. Most functions are not even or odd. Here's an example. If we try and, replace x with negative x here, look what happens. So we got negative x squared plus negative x minus 1. That even exponent means that negative sign doesn't really matter, like we saw before. So we get x squared, and then adding a negative x is the same as subtracting x. So we don't get our original function, right? Because the middle term does not have the same sign. So this is not equal to the original function, which means the function is not even. But it's also not equal to the opposite of the original function, because then all the signs would have changed, but the first term is exactly the same as it was, and the last term is exactly the same as it was. If we factored a negative 1 out of this, we wouldn't get our original function. So this function's not odd either. And you can see that from the table. If you use x values of negative 2 and positive 2, for example, you don't get the same y value, but you don't get opposite y values either. You get 1 and 5. And the graph doesn't have either of the types of symmetry that we looked at either. This graph is a parabola, and its vertex is over here. And so it doesn't have that symmetry about the y-axis, and it also doesn't have that rotational symmetry about the origin either.